So good morning, everyone. Welcome to this one more Athena talk. We are very happy that we have with us Professor Giancarlo Soavi from the University of Vienna. And also this presentation will happen among friends. Athena talks aim to bring together scientists of all the levels from all the topics in order to network, share, the research that it happens all over Europe and beyond Europe. In order to also to work as a brainstorming event for future projects. Today, Giancarlo is going to speak to us about nonlinear light modulation and valleytronics in 2D materials. But before we move and give the floor to Giancarlo, I would like to give a short introduction to him. He has a PhD in physics from Politecnico di Milano in 2015 with a thesis on studying the ultrafast dynamics of quantum confined systems, including carbon nanotubes, graphene nanoribbons, and gold nanoparticles. Since 2015 and until 2018, he has worked in the Cambridge Graphene Center, focused mainly on graphene's ultrafast and gate-tunable nonlinear optical properties and related 2D materials. Since 2019, he has moved to Germany, starting as a junior professor at the University of Vienna. And he has now establishing his own group that they study ultrafast dynamics and nonlinear optics in graphene, transition metal dichalcogenides, and new emerging layered materials, including TMD alloys and layered magnets. So we are looking forward for this presentation. I would like to thank on behalf of Athena Talks, Hellenic Mediterranean University and Athena European University, Giancarlo, for this contribution, and all of you for your presentation. I will request from all of you to mute your microphone, and there is going to be time for questions at the end, unless Giancarlo dictates differently. But the floor is to Giancarlo. Thank you, Giancarlo, very much.
Thank you very much, Kostas. Thank you very much for the kind introduction and also for the invitation. I'm very happy to be here. And let me say, I'm very open if you want to ask questions during the talk. I will not be offended. So if you want to unmute and ask questions during the talk, feel free to do it. So I will try to go straight into the main topic, or let's say to the topic of this presentation, that indeed, as Costa was saying, is nonlinear optics and valleytronics in atomically thin materials. And before I go to the experimental results, there is, of course, a bit of introduction that I have to do. And I want to do it by presenting somehow the main characters of the story that I'm going to tell. And the main characters will be, of course, two-dimensional materials and nonlinear optics. And I start from the most famous among the two-dimensional materials, that is probably graphene. I guess you all know that the research in the field of graphene started, or let's say was boosted by this seminal paper, this science paper in 2004 from the two Nobel Prizes, Gaiman and Novoselov, where they basically built the first field effect transistor based on monolayer graphene. And then eventually in 2010, they got the Nobel Prize for their groundbreaking research, not only for this paper, of course, but also for all the other research that they did in the subsequent years. There is only one thing that I want to point out that would be important for the results that I'm going to present, and is the fact that we have to notice that graphene is really an atomically thin material where we have only carbon atoms in the real space, so in the lattice, which are displaced in this hexagonal lattice. Now, what happens is that if you now take this real space, you have these two atoms, A and B, that are identical in the case of graphene. Now you take the Fourier transform, you go in the reciprocal space, the Brillouin zone, and it turns out that, again, you have an hexagon with your high symmetry points. And in the case of graphene, the Fermi energy lies at the plus and minus K point. So again, at the corners of the Brillouin zone. I see there is one raised hand. I don't know if there is already a question or...
Hariglia, you have raised your hand?
No, okay, maybe it's up.
Sorry, it was a mistake. Thank you.
Okay, no worries. So, okay, there is the Fermi energy lies again at the corners of the Brillouin zone, what we call the K and K prime. And what will be important for us, what we should remember, take home message from this slide, is that at these points, the K and K prime, the dispersion relation is defined or described by these linear bands. These linear bands are equivalent to the Dirac Hamiltonian. This is the Hamiltonian that describes relativistic particles. But this linear band dispersion will also be very important for us when we will do nonlinear optics in graphene. Now, the second main character of this story will be transition metallic chalcogenides. They are again a layered material, but strictly speaking, they are not two-dimensional, because as you see, this time there is a metal atom. Typically, we use molybdenum or tungsten that is sandwiched between two layers of chalcogen atoms. Typically, we use a sulfur or selenide. Now, I want to point out that, again, the real space crystal structure is hexagonal, as in the case of graphene. But this time, the two atoms, A and B, in the unit cell are different. This breaks space inversion symmetry, and this will be highly relevant for what I'm going to discuss later. There is one very peculiar feature of these transition metallic chalcogenides that we will use, and this is the fact, as it was demonstrated already back in 2010 by the groups of Tony Hines and Feng Wang. This is the fact that when you thin down these materials from the bulk form, from the bulk form to the monolayer form, you have a transition from an indirect gap semiconductor. So this is the bulk case where you see the indirect gap is close to the gamma point. You have a transition to a direct gap semiconductors that this time occurs again at the K point. And this is something that you can test or prove by looking at the photoluminescence of the material. Because of course, when you have a bilayer and an indirect gap, the light matter interactions are weak, the photoluminescence, so the light emission is close to zero. And instead, when you go to a monolayer, you have orders of magnitude enhancement in the light emission or luminescence of the material. The peculiar properties of the TMDs that I will use in this presentation is the fact that when you now look at this direct gap, it turns out that this direct gap occurs again at the corners of the Brillouin zone, so the plus and minus K points. And if we consider the fact that space inversion symmetry is broken, it turns out that these 2 points that we call valleys are energetically degenerate, but they're not equivalent. Because in the K and K prime, the top of the conduction band have opposite spin. The top of the valence band is opposite spin. This leads to the so-called spin valley lock. That means we can selectively excite one of the two valleys with a light of opposite circular polarization. And this is the basis of a field that we call the valleytronics. It means that we can use light to selectively generate and read and store information into the spin valley degree of freedom. Okay, the final main character of this story, so the final topic that I have to introduce is nonlinear optics. Nonlinear optics has several different branches, and there are several possible definitions of nonlinear optical processes. In this presentation and in general for my research, I use the definition that is based on, let's say, typical textbook like the Boyd. That is a definition based on the Taylor expansion of the polarization, where the polarization is the response of any material to the interaction with the electromagnetic field. So if the electromagnetic field that you shine on your sample is weak, you typically measure only the linear response, that is this chi1 term. And this is the term that is responsible, for instance, of the absorption or transmission of a material. Now, if you increase the intensity of the light that you shine on the material, typically using lasers, you can have these higher orders in the Taylor expansion of the polarization. And these higher orders are those responsible of nonlinear optics. And in general, nonlinear optics means that you have a certain material, nonlinear material, you arrive with a certain input fundamental beam, you interact with the material, and at the output, you will have new frequencies or new colors that can be done either by harmonic generation or in general by frequency mixing. And again, here I do some bit of shameless self-advertisement. If you're interested in the topic of nonlinear optics in 2D materials, let me suggest a review that we wrote very recently together with Giulio Cerullo, specifically on this topic. So there I think you can find a bit of the state of the art in this field. Okay, now as Kostas was saying during the introduction, this topic of nonlinear optics with 2D materials has been now for some years the core of my research. And nonlinear optics in 2D materials is very interesting because it really allows to span from technology to fundamental science. And we were working in particular on integrated nonlinear photonic devices. So we had examples of photonics devices for logic operations or gas sensing. We also use nonlinear spectroscopy very often for the study of new materials. So as Kostas was mentioning, we work with TMD alloys, Janus TMDs, or layered magnets. But today I want to focus instead on these two other topics. One is the electrical and all-optical modulation of the nonlinearities, and the other one will be the nonlinear valleytronics. So I will start from electrical and all-optical modulation. And here I want to give you two examples of devices where we can tune the nonlinearities. The first one will be third harmonic modulation in graphene, and then I will move to transition metal decoupling. Good. So let's go with the first example. We now take a graphene and we look at the third harmonic generation. So when we take the polarization, we will look at this term, that is the chi3. And third harmonic generation is a process where we arrive with fundamental photons at energy h bar omega 0 and generate photons at 3 h bar omega 0. Now consider that chi2 is 0 in graphene because graphene is centrosymmetric, and this term exists only in non-centrosymmetric crystals. And now if we want to do gate-tunable nonlinear modulator, what we have to do is we have to apply a gate voltage to our material, and with this gate voltage, we have to tune the efficiency of the nonlinear process. And in order to explain how we can do it, I have to include or introduce another element that is typical of nonlinear optics, which has to do with the resonances. Now imagine that you take a gas or a semiconductor, and you do your third harmonic process. So you enter, you arrive with 3 photons and generate 1 photon at 3 omega. Now this process can be either non-resonant, and this is the case where the final state of your nonlinear process is a virtual state that lies within the gap, or it can be resonant. In this case, when you, with your multi-photon, you hit a real electronic transition, and in this case, in the resonant case, you will have a huge enhancement of the nonlinear optical response of your material. Now, you immediately understand that if you try to do this in a semiconductor or a gas, there is no way that you can change the gap, and the only way that you can use to tune the efficiency is to change the fundamental photon energy. Instead, we are looking for a device where we fix the photon energy, so we fix the light that we shine on the material, and we change the efficiency by applying a gate voltage. And this is why the linear band dispersion of graphene comes into play, and it's very useful, because now you can imagine that your Dirac cone is or allows for all the possible resonances that we want. And we can start from a condition where the Fermi energy lies exactly at the center of the Dirac cone, that we would call the non-resonant condition. And now clearly by applying a gate voltage and tuning the Fermi energy, we can move across these transitions that would be 1, 2, and 3 photon transitions, as shown in this sketch. Now, this also translates in a theory, or in the theoretical graph that I show here at the top. Here on the y-axis, we have on a logarithmic scale the third harmonic generation efficiency. So how much a third harmonic you generate for a certain input power. And on the x-axis, as you see, we have the Fermi energy divided by the photon energy. Now, clearly, if you fix the photon energy, h bar omega, moving on the x-axis here is equivalent to tuning the Fermi energy. And now you see that already the theory tells us that as we tune the Fermi energy, we will have 3 peaks that are very sharp and very clear, that are indeed these 1, 2, and 3 photon resonances. So this is how theoretically graphene could work as an electrically tunable nonlinear modulator. And this is the experiments that we did now some years ago already. Luckily, this is relatively simple because now you can take a graphene on a silicon dioxide. So basically you build a graphene field effect transistor. You apply a gate voltage. The gate voltage translates into a certain Fermi energy. We fix the fundamental photon energy to 0.6 electron volt. The third harmonic is at 1.8. And you see that by changing the Fermi energy, we have a very strong change in the third harmonic intensity, that is our y-axis. And in order to make this graph a bit easier to read, I now take each of these curves, calculate the total intensity, and plot it on this graph now on the right, where we have on the top x-axis the gate voltage, the bottom is the Fermi energy, and on the y-axis we have the third harmonic intensity. And you see that when we are close to 0 Fermi energy, this is what we call the non-resonant case, the third harmonic is very weak, close to 0. And then there is this special point at the dot line where the Fermi energy is half of the photon energy. And from here, we have this very strong increase in the third harmonic generation efficiency. Now, I want to point out, if you look at this graph is the first demonstration of gate-tunable nonlinear optics in graphene, so gate-tunable third harmonic generation. Note that we only go from 0 to negative values of the Fermi energy. And this is a limitation of the samples that we were using and the fundamental photon energy that we were using. So we only see enhancement in one direction, and we cannot probe this part here. This will be important in few slides from now. Okay, so basically this experiment showed us, as I said already a few years ago, that graphene is the ideal platform for gate-tunable nonlinear optics, because now we can fix the photon energy, apply an external gate, and with that we can switch on and off the efficiency of the third harmonic with very large on-off ratios. Now, typically at this stage, I would ask if anyone has questions, but I do it when I'm delivering lectures in presence, because I like to see the faces of the people when I ask these questions. So in this case, I will just move on and tell you. Yeah, Kostas?
Yeah, I have a question. Thank you very much for the presentation for the moment. I would like, this, application of the voltage, the external voltage in order to tune and translate, the energy, the Fermi energy. Is not a disadvantage at the same time. It's an advantage since you are creating, you have an impact on the efficiency of the third harmonic generation, but from the energy consumption, it's not considering disadvantage. It's like to create a threshold, that you create a threshold.
What do you mean you create a threshold? Sorry.
In order to start up, the initiative. I mean
So that's a point, but it's not necessary, because, for instance, if you look at this graph, actually you can also see it from here. You see that the material was already highly doped, right? Because when we use the zero voltage, the material was already at 0.3 electron volt. So the highest efficiency is in the case where you have a large doping. And this, in graphene, you don't necessarily need to go to apply a gate voltage. You can also do chemical doping.
Yes.
So if the only thing that you want to do is to have a high nonlinear response, I would tell you, take the largest possible doping, put whatever you want dopants on your graphene, and you will get a much larger response.
This reminds me, with the periodically poled crystals, how you translate them in order to enhance the intensity of the of the output. Okay.
Yeah. Okay. Yeah. I think there are also other two questions. So
George,
I'm happy to questions
Kavellakis was first, and then provide the floor to Kourmoulakis.
Hello, Giancarlo.
Hi, George.
Thanks for a nice presentation. I would like to ask you specifically for this right-hand graph. Why do you stop your scanning at minus 0.6 electron volt? Is it because the bands stop to be, they are not linear beyond this level?
These certainly the bands will not stay linear for longer, but I will get to that. The limit is the voltage that we can apply. So if you see here, we already go minus 150 plus 150, and this only works because the oxide that we are using is at 300 nanometers. Beyond this 150, you just break the device. I will show next results on a different device, different photon energy, and I will get back to that in a few minutes.
Thank you. Thanks a lot.
And George Kourmoulakis, please.
Yeah. I have a more fundamental question, maybe. So you saw, Giancarlo, you showed previously that when you when you arrive with your photons, when you are off resonance, you reach a virtual level. But when you are on resonance, you reach a real energy level. Is there any absorption involved? The phenomenon, the photons are absorbed, and if they are absorbed, is there any non-radiative relaxation happening before you get back your photon?
So it is a very good point, but I would go back to, in general, the theory of nonlinear optics. So the fact that you can have an enhancement when you are at resonance is something that it's true for any material. And indeed, the materials that are used for nonlinear optics, typically like BBO, KTP, periodically put, they must be fully transparent. So if you want to use a bulk material, you can never go on resonances. And the problem is not for the fundamental photon energy, which is always in the transparent region. The problem is that if you now generate a third harmonic or second harmonic at a certain resonance, and then you propagate inside the crystal, the emitted harmonics will be reabsorbed by the material in a linear fashion. So basically at the output, you will get zero. So this trick of using resonances only works in atomically thin materials, so graphene and TMDs, because there the reabsorption is close to zero. So exploiting the resonances is, of course, one way of enhancing the nonlinearities, which is known also for bulk materials, but you cannot apply to bulk materials, right? You can only apply it to TMD or to 2D materials.
Okay. Thank
you. Can I also ask you a question, please?
Sure. Sure, yeah.
What about the linear process, this Chi1? Is it not also present here?
So
because presumably...
It is certainly present, and maybe I might mention later where Chi1 plays a role in the next slides. I mean, it plays a role in the efficiency of the nonlinear optics, but in a very indirect way. So maybe I will go to the next slides to show why the Chi1 plays a role, if you agree.
Okay, thank you.
So maybe I start from these questions to go on. But before I move on, I want to show one thing, and the thing is the following. I started from discussing this theory, where I say, okay, there are 3 very sharp resonances, and the first resonance is when the Fermi energy is equal to 2 times h bar omega, this one. And now we look at the experiments, and this line, that is exactly this condition here, it's certainly not at the point where we have a resonance. So there is clearly a very big discrepancy between the theory and the experiments. So now you should argue either our experiments are wrong, or our interpretation is wrong, or something is missing. And let me tell you that the answer is that something is missing, because until now I was a bit cheating, and the theory that I show you is a theory that is developed that works only when the electronic temperature is equal to 0 Kelvin. Now, 0 Kelvin is something that does not exist in experiments. So if you now extend the theory to certain values of the electronic temperature, you get these other colors of the curves, and you can sort of easily understand what is happening by considering that as you increase the electronic temperature, you broaden the Fermi-Dirac distribution, and this broadening of the Fermi-Dirac distribution broadens these very sharp peaks. They merge into this sort of a featureless modulation of the high harmonics. And to understand why this is so relevant in nonlinear optics, we should also understand what are hot electrons and how do they evolve. Now imagine that initially you have graphene at equilibrium, then you arrive with a very short pulse that breaks this equilibrium. And you can imagine that at the very beginning, the system will be in a so-called out of equilibrium condition. That means you have delta Diracs in the upper and lower cone. This cannot be described by the Fermi-Dirac distribution. Now, next, you have electron-electron scattering, and this builds up the so-called hot electron distribution. So it's a situation where the electrons are described by the Fermi-Dirac statistics, but this time with a very high electronic temperature. And finally, by electron photoscattering, you relax, so you transfer the energy to the lattice and generate, or let's say, electrons and lattice will have the same temperature. Now, when we do our experiments of third harmonic, we use pulses that are very short, in the range of 100 femtosecond. The third harmonic is generated only within the pulse duration, and this means that in our experiments, the situation or the electronic distribution is dominated by this very high temperature. And now, if we take again our experimental data, so the white points, and overlap them with the theoretical curves, but this time we use higher electronic temperatures. I don't plot the 0 Kelvin, I start from room temperature, 300 Kelvin. You see that our experimental data, they are also very far from 300 Kelvin. This is a logarithmic scale. And instead they sit, so they fit quite well with temperatures that are in the range of 1000 to 2000 Kelvin. And now I go back to the previous questions. Where does the linear response, the Chi1, play a role? The Chi1 play a role because the fundamental beam is absorbed, and by absorption, it will increase the temperature. And this increase in the temperature is what changes eventually the efficiency of the nonlinear process. And since we know that also the absorption of graphene is gate tunable, because by tuning the voltage, you can move between intra and interband absorption, you see that as we cross this point, the experimental data do not follow any theoretical curve. And this is because the theoretical curves are done for a fixed temperature, while the real experimental temperature changes as you change the Fermi energy. And this is because the Chi1, the linear response, is a function of the doping and the Fermi energy. So If this is clear, so if it's clear the fact that the hot electrons play a key role, then we already understand how we can implement now not an electrical modulator, but an all-optical modulator. And the idea is the following. We can now fix, with the gate voltage, we can fix a certain Fermi energy. Then we add another pulse that we call the pump or the control pulse. And with this one, we only change the temperature. So the pump pulse will be absorbed. We will change the temperature of the sample, and the temperature will affect the efficiency of the third harmonic. And before I start with that, I point out that this time we are using a different type of device. We don't have only graphene on silicon dioxide, but this time our graphene is encapsulated in hexagonal boron nitride, so much higher quality. We changed the photon energy to 0.3 electron volt. Now I go back to the question of George. You see now the silicon dioxide is much thinner, it's 90 nanometers. So here we apply gate voltages of around plus minus 30. The graphene is encapsulated, so the Fermi energy lies at 0 gate voltage, the material is undoped. And now you see this curve that I like very much, it's very beautiful in my opinion, where we can see that the enhancement in the third harmonic, there is no pump pulse, this is only gate tunability, but now the enhancement can occur symmetrically in the p-doped and n-doped region. And this is a clear indication, I think this is the nonlinear analogous of the ambipolar field effect transistor and ambipolar field effect behavior that tells us that there is a full analogy between electron and holes within the Dirac cone. And this is what we can observe here for the first time. But now let's move to the all-optical modulation. Now the idea is the following. We use the gate voltage to fix the Fermi energy, and then we arrive with the control pulse. And now I plot here on the y-axis how much I'm changing the third harmonic. This graph is normalized because I only want to focus on the dynamics. And on the x-axis, I have the time scale, so the delay between the control pulse and the fundamental beam. So time 0 means the control pulse arrives together with the fundamental beam. Here you see there is a very rapid drop in the third harmonic efficiency, and then a certain recombination dynamics that takes something in the range of picoseconds. Now, this recombination dynamics represent this sequence of events that I was discussing before. And if you zoom in, you will recognize that there are mainly two dynamics at play. The first one is very fast, it takes approximately 100 to 100 frames per second. And this is typically attributed to this process here, the electron phonon scattering. So the electrons that couple to the optical phonons of the material. However, in every material, there is always a slower component that takes a few picoseconds. This was originally attributed to the so-called super collision scattering. That means hot electrons scatters with the defects inside the sample. Now, very recently, Clasti and Roy gave a different explanation, that is, this long decay is, or let's say, is due to a coupling between the optical phonons and the acoustic phonons. But what is interesting for us is that if I now change the Fermi energy, the dynamics change completely. And in particular, the main difference is not in the slow component that is always there, but it's in this initial fast component that basically disappears as we go to large values of the gate voltage. And now we know why this is happening. This is again a work that we did with Giulio Cerullo. And the idea is the following. When you generate hot electrons, that means electrons that lie at high energy in the Dirac cone, if you want to dissipate energy to the lattice, you have to decay into the Dirac cone and emit an optical phonon. However, if you now start increasing the doping, there will be a level where the final state where the electron should go is already occupied by another electron. This is a sort of polyblocking or a phase space filling or a phase space quenching. So in this case, you cannot emit an optical phonon anymore. And then, of course, this dynamic must be fully suppressed. And this is indeed exactly what we observe also in these third harmonic experiments. There is one final thing, now that we know that we can have this tunability. So now I told you that in graphene, we can control the third harmonic electrically, and we can change the modulation. We can control the dynamics because we can make it slower or faster depending on the value of the Fermi energy. And we can also control the total amplitude in an all-optical fashion. Because now you see that the third harmonic modulation, so if you take the maximum of these dynamics, here it's all normalized, but here you see it in percentage, then if you increase the pump fluence or the fluence of the control pulse, of course you change the maximum modulation depth, but the maximum modulation depth is also a function of the doping or the Fermi energy. And I just want to point out that this is highly nonlinear. This can be fully explained if you consider the nonlinear response of the material. But I want to point out that you can reach very large values of modulation, up to 90%, if you go to large values of the Fermi energy and sufficiently large values of the fluids. Okay, so for the third harmonic, we have a full control. I would like now to move to the next topic, unless there is urgent questions. Otherwise, I will go to second harmonic. I'm also happy to take questions at the very end, of course. So time is running, so I will move to second harmonic modulation in TMDs. Now, the idea is very similar. We again want to have a modulator, so a device where we switch on and off the nonlinearities. This time, we will be looking at the second harmonic because, again, as I said, we have an hexagon, but the two atoms in the hexagon now are different. So the symmetry, space inversion symmetry, is broken. In this case, we can have a Chi2. We can do second harmonic generation. So we enter with 2 photons, generate 1 photon at 2 omega. Before I tell you what we did, maybe a brief state of the art. So when we started this project, there were already 2 main approaches to tune the nonlinearities in the transition metadical coherence. The first one is the electrical modulation. Even here, there are different possibilities. The one that I like the most is the one that is based on breaking of space inversion symmetry. So now you can take a bilayer. Bilayer TMDs are centrosymmetric. You can now apply an out-of-plane electric field. And with this out-of-plane electric field, you break the symmetry. So now you see that as a function of gate voltage, you have a very large tunability of the nonlinearity. The advantage is that on-off ratio is very large. So you see this goes, I mean, this is a factor of 60. The problem is that electronics is intrinsically slow. You can never switch on and off your signal at sufficiently high speed because you will be limited by your capability of switching this electric field that typically is at a maximum of nanoseconds. And that's why people go to the all-optical modulation. That is, you modulate the efficiency with an optical pulse. You see this graph reminds what I showed before about graphene. The time delay is the delay between the control pulse and the fundamental. Here, they're modulating the second harmonic in TMDs. You see now the dynamics are a bit slower. They are tens of picoseconds. And the idea is that the second harmonic must be resonant with the band-to-band transition, so with the exciton of TMDs. The control pulse generates electron holes in the valence conduction bands. And as you generate these new electron holes, you reduce the let's say, the strength of your optical transitions, and the second harmonic will be quenched. So now the advantage is that the speed is much higher. The disadvantage is that the modulation depth is lower, but there is another big disadvantage, that this method is now very narrowband. So this method only works if your fundamental beam or your second harmonic is at resonance with the exciton. Otherwise, you cannot have any quenching. And this is where we came with our idea, where we thought, okay, is there a way of combining the best of the 2 approaches? So very large modulation depth and very high speed with an ultra-broadband bandwidth. And this is possible, and our idea was to do it using the symmetry of the materials. Now, I should tell that if you look at this hexagon at TMDs, you can assign this to the so-called D3H point group or crystal symmetry. And I don't go into the details, I only focus on the fact that you see there is a high symmetric direction, that is the one that connects the metal atom to the chalcogen atoms. This is the so-called armchair direction. And of course, you can rotate this hexagon by angles of 120 degrees. That is 2 pi over 3. This is the reason of the 3 in this letter number here. So if you divide by 120, you always end up in the same symmetry. So there is clearly a symmetric operation that is 120 degrees rotation that brings me in the same condition. Now, if you take this point group and look at what happened to the second harmonic, it turns out that if the 2 photons that contribute to your second harmonic signal are both aligned along the armchair or both aligned along the zigzag, then in both cases, your second harmonic is emitted along the armchair direction. However, if you split the 2 photons that generate the second harmonic, one along armchair, one along zigzag, then your second harmonic will rotate by 90 degrees and will be emitted along the zigzag direction. So now the idea is the following. We take 2 replicas of the same paths and we align them orthogonally polarized with respect to each other, one along the zigzag, one along the armchair direction. Now, we generate second harmonic, we place a polarizer in front of the detector, and what will happen is that if the two pulses are far away from each other, as you see in this graph, the delay is larger than the pulse duration, then nothing will go through the polarizer, so the signal is identically zero. And now you change the delay, the two pulses overlap, you rotate by 90 degrees the polarization of your signal, everything is transmitted through the polarizer, and you have a maximum in the second harmonic. So with this very simple approach, we get the largest possible modulation depth, really 100%. The highest possible switching speed, because this time we are not limited by the dynamics of the excited state, but only by the pulse duration. But we also get the largest possible bandwidth, because now you can do this for any wavelength that you want, and you don't need it to be resonant. And now if you want, this approach is somehow the equivalent of a half-wave plate. So this TMD is a very efficient nonlinear and ultra-fast half-wave plate, where you can rotate the polarization by 90 degrees on a time scale limited by the pulse duration. And it turns out, this is something that we did in collaboration with Isabel Staude in Jena, that if you have an ultra-fast half-wave plate, that is our TMD in the nonlinear optics regime, and you combine it with a passive metasurface, then this total optical element can be used to tune the wavefront of light. So now we can play with this device to achieve on an ultra-fast timescale beam steering, Gaussian to vortex beam tuning, but even tuning of the orbital angular momentum. So these nonlinearities of the TMDs are also very powerful if you then want to combine it for complex light structuring and light shaping. Okay, so this was the end of the first part, and now I will try to move quickly to nonlinear valleytronics, but Kostas, if at some point I go too long, feel free to stop me and I will cut any part.
Giancarlo, you have 10 more minutes, and
okay.
5 minutes for the questions. Thank you.
Okay, so I will go to this nonlinear valleytronics. There are even here two topics. If we see that we go too long, I will skip the second one. But let me start quickly with the detection of a Valley polarization. We started from the idea that, as I was discussing, valleytronics in TMDs is very interesting. And it's very interesting because it combines inversion symmetry and time reversal symmetry. And it's also interesting for applications because the spin valley locking allows to write, read, and store information into the valley degree of freedom. Now, there is a problem that nowadays, if you want to read a valley imbalance, what you typically do is you measure a photoluminescence. So those of you, I know George, who is working with valleytronics or valley, you typically measure photoluminescence. That means you generate a valley imbalance, so you put excitons only in one valley, and then you wait for these excitons to recombine and check if the emitted luminescence is secretly polarized. Now, this method is not the ideal one because this method is slow. You have to wait for the recombination, and it's destructive. The moment that you emit light, the valley information is lost. So is there a better way of measuring the valley degree of freedom using nonlinear optics? The answer is yes. And for that, I go back to the polarization and I focus on this term, the chi2, that I only mentioned before. It's the second order nonlinear response of the material. Now, if I go a bit more into the details, sorry if there is a bit of algebra, but this expression here basically tells you that if we know that we have three armchair directions, and we know what is the polarization of the incoming electric field, so the incoming electric field can be either along zigzag or along armchair or along a superposition of the two, then the second harmonic will be emitted either along zigzag or along armchair. This graph here, the so-called six-fold pattern, is an experiment where you rotate the polarization of the excitation and simultaneously you rotate a polarizer in front of the detector. So you always measure a second harmonic that is parallel to the input. Now, this graph tells you that there are three directions of high symmetry that, of course, are the armchair directions. And this is basically to say that if you excite along the armchair direction, the second harmonic will be emitted along the armchair direction. This is the case where the material is at equilibrium. So there is no valley imbalance, time reversal symmetry is preserved. Now you break time reversal symmetry, you reduce the symmetry of the system, you will have new terms into your nonlinear tensor that we call valley polarization terms. Now, from this matrix, you can immediately observe that these Valley polarization terms are orthogonal with respect to the intrinsic response. In other words, now there is a new element or a new second harmonic that if you shine along the if you excite the sample along the archer direction, you emit second harmonic along the zigzag. So orthogonal to the intrinsic response. Overall, this six-fold partner will be rotated by a certain angle, delta or theta, and this angle is a direct fingerprint of Valley imbalance and broken time reversal symmetry. So how do we do this experiment? We go on WSE2 and we shine elliptically polarized light. Now, this elliptical polarization is the perfect superposition between a circular component that breaks time reversal symmetry, so generates the Valley imbalance, and a linear component that we use to read the Valley polarization. And here are the experiments. Let's say that we start from a linear case. The input is linear, polarized along the armature direction. So this is a polar plot. 0 is the armature direction. The output, the red curve, is again linear, as you can see, polarized along armature. Now we go to elliptical beam, and you see the output is elliptical because the circular input, circular fundamental turns into circular second harmonic. So this is something that we cannot get rid of, will always be there. But the interesting part is that the ellipse now is rotated with respect to the input. And this rotation is because the linear component of the ellipse is tilted in one direction. There is an angle minus θ. And interestingly, if we change the direction of this ellipse to the other side, the rotation will be in the opposite direction. And this is a clear indication that with the different circularly polarized light, we excite either K or K prime. Now imagine that you do these experiments for different values of the ellipticity. This is the zero line, no rotation. We enter linear, the output is linear. But you can clearly see that as you change the ellipticity, you can go to positive or negative values of a second harmonic rotation. And if you do some algebra, it turns out that this angle theta is directly proportional to the ratio between the Valley polarization and the intrinsic electric dipole nonlinear response. And now, of course, you can do this for different values of the wavelength. I was only talking about the resonant case, where we go at 1.5 micron that is resonant at 2 omega with the exciton. But if you do it below gap or above gap, it turns out that when you are at resonance, and this is probably obvious because this is when you're really probing the valleys, then you have a rotation angle that is 1 order of magnitude stronger compared to the off-resonant case, so above and below gap. Okay, so this is a very powerful method, and there is one additional element that I want to mention, and then in the last 5 minutes, I will try to tell why this is important, and it's the fact that while the electric dipole response, so the nonlinearity coming from broken space inversion symmetry, is constant with power, it's an intrinsic property of the material, the one coming from broken time reversal symmetry is a function of the power. And this is because we break time reversal symmetry, so we generate the Valley imbalance with the same pulse that we use to read the Valley imbalance. So for this reason, as we change the intensity of the power that we shine on the sample, we change also the rotation angle because we induce a larger Valley imbalance. And it turns out that the type of, so let's say the scaling of this term with the fundamental power is linear. And this, I'm not going to the details. If you're interested, we can discuss this in the question session. This is a clear indication that we break time reversal symmetry by the coherent optical Stark effect. So not by a real excited state population, but by off-resonant and ultra-fast coherent process. And now this also tells us another thing that I will use for this Valley polarization interference, that is the following. In the experiments that I told you, that I show until now, basically we have to shine elliptically polarized light because the circular component breaks time reversal symmetry and the linear component measures the rotation angle. However, this method is again not the ideal one because if we really wanted to selectively pump the Valley, we should shine circularly polarized light on the sample. So the perfect excitation is when we shine circularly polarized light and we can be selectively on K or K prime. So the question is, can we use a circularly polarized light to measure the Valley polarization? With this method, certainly not. because the moment that we go circular, we cannot measure the rotation angle anymore. So we are lost. But what happens if we shine circularly polarized light? And I want to explain the case with this sketch. Let's say that we start from a material that is at equilibrium, so no valley imbalance. We arrive with linear polarization. Linear polarization is a perfect superposition between left and right circular polarization. Each of them will excite one of the two valleys in a perfectly balanced way. Time reversal symmetry is preserved. The output will be linear. In this case, the electric dipole, that is broken space inversion symmetry, gives the second harmonic. The valley polarization, that is time reversal symmetry, is preserved. The system belongs to this D3H point group. If we now shine circularly polarized light, the point group changes because we are breaking time reversal symmetry. Our second harmonic comes not only from the electric dipole, but also from the valley polarization. Now, I want to convince you that if you take the ratio between the intensity when you shine circularly polarized light and the intensity when you shine linearly polarized light, this ratio contains information about the valley polarization and about the broken time reversal symmetry. Again, for this, we will need a bit of algebra, but I will skip it and go quite fast. Let me only tell you that if you calculate this ratio, assuming that there is never valley polarization, not even in the circular case, so time reversal symmetry is always preserved, then this ratio, circular to linear, should always be equal to 2. And this, let me tell you, is the assumption that every people doing nonlinear optics into the materials has been used until now. Now, if you consider that the circular polarization breaks time reversal symmetry and induces a valley polarization, the ratio will be very different from 2. And in particular, you can have an element that goes like the square of the ratio, valley to electric dipole, and something that goes linearly with the ratio plus an interference term. This interference term only arises and only comes into play if you consider that these elements are complex and you have a phase shift, so real imaginary part, between electric dipole and valley polarization. Now, if we look at the power dependence of this ratio, so eta is the ratio, 2 means there is no broken time reversal symmetry. Instead, you see that the ratio is different from 2 and scales linearly with the power. Since we know that the valley polarization is linear with the power, this term should go quadratically with the power. This term go linearly. So from this, we can already tell the quadratic term can be neglected. And this is because the valley polarization is smaller than the electric dipole, approximately a factor of 10. So this will be a factor of 100, this will be a factor of 10, this one dominates. But what is very interesting is that the ratio between the two is very different from what you would expect without a broken time reversal symmetry. And it can be both larger than 2 or smaller than 2. And this is something that you can only explain if you consider the interference between the electric dipole and the valley polarization. And now let me tell you, if you do a scan of the wavelengths across the excitonic resonance in WSE2, so the orange curve is the photoluminescence of our material. So exactly when we have the linear response, the absorption or the emission of the material, and you see that the ratio, this eta, it's never 2, and instead it has a shape that is very similar to the first derivative of the absorption. So it's very similar to the imaginary part of the linear refractive index of the intrinsic response of the material. I find this very beautiful for several reasons. First one, this is a method that allows us to probe directly broken time reversal symmetry in TMDs while being perfectly selective with the valleys, because now we can really shine circularly polarized light and measure the nonlinear response. But to the best of my knowledge, this is also the very first demonstration of interference between broken space inversion symmetry and broken time reversal symmetry in a TMD. That is the analogous of a magnetic field or pseudomagnetic field. Okay, so sorry if I was a bit long. To summarize and very briefly, the experiments that I was showing you today: electrical and all-optical modulation of third harmonic generation in graphene. Electrical modulation because we can move across multi-photon resonances by tuning the Fermi energy. All-optical modulation because the electronic temperature has a very strong impact on the third harmonic efficiency. Then I show you modulation of second harmonic generation in TMDs. This is based on symmetry considerations. And this is also what we use now for generation of vortex light and tuning of the orbital angular momentum. And finally, these new emerging fields of nonlinear valleytronics, where we can use the second harmonic generation to detect the presence of a valley polarization, but even more interesting, where we can measure the interference between space inversion and time reversal symmetry in these atomically thin materials. So with this, I would really like to conclude. Of course, thanks all the members of my group that did most, if not all, of the work that I was showing today, the funding agencies, but more importantly, I would like to thank all of you for your attention.
Thank you very much, Giancarlo, for this very beautiful presentation. Please stop sharing the screen to start, the questions. I think that we have 5 minutes for questions, but this is the official schedule. I mean, depends on Giancarlo's availability and the number of questions that we have. Any questions from the audience? I would like, George, from your body language. Okay, so I will give you some time. I have some questions, Giancarlo. I would like very much, I like your observation regarding how this efficiency follows the derivatives of the absorption. But if you go back, even though that the absorption looks very symmetrical, these inclinations, they follow during, the rising, a different inclination, but there is a tendency with different, completely different inclination towards, the falling of the photoluminescent signal. Why do you think that this happens? I mean, they follow the tendency, but, they are completely different,
Maybe I can share the screen again for a second.
Exactly.
So you see the screen, no? You mean
yes,
right?
Yes.
So that's a very good point. To be fully honest, we still don't know, right? It's something that we still have to investigate. However, what I can mention is that, so as I said, the shape that we read here is the interference between the intrinsic response, so let's say the image. So we can do the following. We can assume that the electric dipole response, so the response coming from broken space inversion symmetry, is mainly imaginary. Because we know that when we are close to a resonance, the refractive index becomes almost purely imaginary. And this will be similar to the derivative of the absorption. However, this is not exactly the case, because the exact shape of this one will depend on the quality of the material and on the substrate. And this comes directly from the Kramer-Stroening relations. And this is something that we did not calculate, right? We have this material, we have the photoluminescence, we did not go in details up to the Kramer-Stroening relation. The other thing that I should mention is that this shape depends on the interference between the valley polarization and the intrinsic response. So while for the intrinsic response, we can look at the absorption and we can somehow estimate what we would expect, for the time reversal symmetry, we don't have any benchmark, no? I mean, there is no measure, except for this one, that is the only one that I know. We have no measurements from which we can retrieve the real and imaginary part of the, let's say, susceptibility coming from the valley. And I think this is somehow the difficulty in understanding this. So the next step would be, first, characterize perfectly the intrinsic response, real and imaginary part. And then from this graph, we can derive the valley polarization refractive index. But we didn't go that far. It's challenging. We didn't go that far.
And based on this measurement that I respect, it's very reliable. No, I mean you repeat it a lot. Do you think that gas sensing can play an application? Since then, with your material, the agent that you would like to detect can influence, the value of this. Because you mentioned something about the quality of the material.
Yeah. So that's a very good point. I would tell, certainly the presence of gases will change the linear response, right? Because it can give doping, it can reduce or enhance, so definitely can be measured. I don't know whether this would be the most sensitive way to measure it, right? But, so, I mean, if you only want to measure the presence of a gas, then maybe there are methods that are more sensitive. This could do it, I think, but maybe not the most sensitive.
Yes,
There is something that only this method could do, probably. For instance, if you have a type of adsorption, right? So a type of gas that maybe gives a certain spin orientation. So I don't even know if it's possible, but you have an adsorption and this orients the spin in one direction. Now, this is a type of adsorption that breaks time reversal symmetry, right? And now this technique could tell you if the gas that you adsorb generates a spin imbalance or not. This, I think, is something unique that other technique that only look at the shift in the absorption could not do.
And these measurements that you are taking at the room temperature, what is the temperature?
Yeah, this is, I mean, this is room temperature, non-encapsulated, so the quality,
Excellent.
I mean, the valley is always there, right? But of course, we will also repeat it on high quality, low temperature. This is very fresh. What I showed here in the last part is, it's very recent, so we are still working on it.
Thank you, Giancarlo. There is a question. Unfortunately, I have a number and not a name from 403-952-0498. And he asks, how can you differentiate the defect part in TMDs? Am I right?
Yeah. So that's a good point. Thanks. I have to say, so as I was saying to Kostas now, for the experiments that we do at the moment, we don't look at defects, but because we work with non-encapsulated material and at room temperature. So typically, the features that we observe are very broad, and any other type of quasi-particles, so trials, bi-exciton, defects, they all fall within the broad absorption, the broad Gaussian or non-homogeneous absorption that you have in these materials. Of course, when we will repeat the measurements in encapsulated samples and cryogenic temperatures, then by scanning the wavelength, we will also be able to go selectively on defect state, trions, exciton, bi-excitons. And this, I think, is also very interesting because, for instance, one question that we could answer with this technique is what is the valley, what is the valley intensity, what is the nonlinear valley term for a defect with respect to a neutral exciton. So do you have more valley imbalance or do you have less valley imbalance? This is something that for sure we could do. And we can do it in a time-resolved way. I didn't show it now, but our pulses are ultra short, so we can also, of course, look at the dynamics.
Thank you very much, Giancarlo, for the response. I hope that our colleague 403 and etc. Is happy with this answer. In different case, please come back. Any other question from the audience? I have another one that I like very much your approach regarding how do you elevate the temperature with this control pulse. I would like to ask you, somehow you have answered, in your presentation, but I would like to have, I'd like to reconfirm some thoughts that I have. How much this control pulse and the impact that it has in this modulation depth, am I right that you have generated? Is like the pulse duration and the number of pulses. Are you talking about a single pulse or you are talking about a number of pulses? Because we know that the temperature effects are accumulative. So probably you can use attoseconds, but a lot of pulses, and you can, induce some modulation depth. So what is your comment on this?
So that's also an excellent point. So let's start from the pulse duration. So the pulse duration makes a difference, and our benchmark should be the pulse duration with respect to the processes that define the recombination. So if we can do this with an extremely short pulse that is shorter than electron-electron scattering, for instance, that is typically, people believe it's in the range of 10 femtosecond in graphene, then you could see even different dynamics, right? Because the third harmonic would change even in a different way. If you take a very long pulse, 10 picosecond, then within the pulse duration, the electrons have time to relax or to transfer the energy to the lattice. So the modulation will be extremely weak, right? Because basically, with and without pulse, there will be almost nothing. Regarding the number of pulses, this is, of course, an issue that we somehow observe, but it's not critical, in the sense that we do experiments at 80 megahertz. That means the distance between two subsequent pulses is approximately a bit more than 10 nanoseconds, so 13 nanoseconds. Of course, you can have some effect of accumulation, so you can heat up the sample, but the way we do it is that you will reach a steady state condition. So the sample maybe will not be exactly at room temperature, but will be at a slightly higher temperature. And this is our new offset. Now, between the two pulses, that is 13 nanosecond, the response of graphene really goes to zero, because after 10 picosecond, something like that, the pump probe signal of graphene has completely gone back to zero. So we can assume that between two pump pulses, the graphene itself has gone back to zero. The fact that we are not exactly at room temperature, that's true. But at the end, what matters for us is the differential change. No? So the fact that pump on, pump off, we have a big jump. Indeed, we could try to repeat these measurements into a cryostat. Actually, we did also the same measurements in a cryostat. And the only thing that you're doing is you're shifting the offset. And by doing that, you can get slightly larger or slightly lower efficiency, but it's not changing the physics. That's what I mean.
Thank you very much, Giancarlo. And this generates me, another question, if you don't mind.
Sure, sure. Right.
I mean, there are some properties regarding how the graphene manages, the temperature. And this is actually one of its advantages. So here you induce a temperature change for graphene. If you repeat the same experiment, let's say with TMDs, I mean, if this is possible, that they have a completely different, kind of physical properties regarding this temperature management. What do you observe? Do you observe harder way in order to induce this modulation depth? I mean, because you need to induce this modulation depth. So how, these measurements, I mean, is the modulation depth that changes the impact of the effect?
Yeah. So the temperature has a direct effect on the modulation depth. I have to say that, I mean, I didn't want to go too much into the details, but now we know that it's not only the temperature, but there is also polyblocking that plays a role. I would say that rather than changing material, which is of course possible, what we can do or what one can do is to change the conditions around graphene. And I say that because if you would do the same in a TMD, for instance, then in a TMD you have a band gap. So even if you have a very large electronic distribution, at some point, the Fermi distribution would fall into the gap, and then you are limited in the amount of changes that you can do, no? Because your electron distribution is always the product of the density of states times the Fermi distribution. And this is one of the beautiful things of graphene, that except for the Dirac point, the density of states never goes to zero. So when you calculate your real electron distribution, you can really go from zero to whatever point of the Dirac cone by simply changing the temperature. That's why the effect is even stronger in graphene. What we can do, though, is we can use some external parameters to change the recombination dynamics. And I didn't mention it, but graphene encapsulation with hexagonal boron nitride is one of those. Because, for instance, we know that graphene, so hot electrons in graphene have a very strong coupling with the hyperbolic phonons of hexagonal boron nitride. So there is a very efficient dissipation of heat into the out-of-plane directions. And the other way that we can use is the gate voltage, because as I was discussing, with the gate voltage, you can quench the scattering with the optical phonons. No? So this is, for instance, I mean, in my opinion, showing that as you change the gate voltage, you change the dynamics and you change consequently the temperature. I think this is already a very nice manifestation of how all these parameters contribute all together to the final nonlinear response.
Thank you very much. George, the floor is yours.
Thank you, Giancarlo, for the very interesting presentation. Of course, the last part is very exciting to me. I look forward for the published version of it. I have two questions. The first one is on this subject that we are discussing right now. Is there any impact? You said that there is a coupling with the optical phonons. Do acoustic phonons play any role in this process?
So, in theory, electrons cannot couple directly to the acoustic phonons. I mean, because acoustic phonons at gamma, so at zero momentum, acoustic phonons have a zero energy. So there is no phonon, right? If you would couple to an acoustic phonons, this has to be an acoustic phonon that has a certain momentum. And in that case, if you want to scatter with an acoustic phonon and conserve the energy momentum, either you need to have a defect that then brings you back at zero momentum, or you need a double scattering, no? Where you go plus K, plus Q, minus Q. And that's why electrons cannot directly scatter or directly couple to, let's say, to acoustic phonons. And that's why typically we assume that the initial scattering is with the optical phonons, unless we consider this theory that I mentioned before, the super collision scattering. There was indeed the idea that there is always a certain probability of scattering with a defect plus an acoustic phonon. Now there is class thyroid, that there's this idea that what matters is not really, that you can always have this sort of direct coupling between the phonons, so optical acoustic, that in a sort of indirect way connect to the hot electrons.
Thank you. And the second question that I have is more technical. Mm-hmm. In the part that you excite the material to probe the valley polarization with elliptical polarized excitation, the technical thing is how do you generate this elliptical polarization?
Quarter wave plate.
Quarter wave plate. Can you change the magnitude of ellipticity?
So the parameters that we can change are, of course, if we change the total intensity, we can change the total intensity of the input, and by rotating the angle, so the fast axis of the quarter wave plate with respect to the linear polarization of the input, we change the ratio between the main axis and minor axis. So you go from a case where you are only linear to a case where you are more and more elliptical until you become circular, and then you go back in the other direction.
Okay.
That's a technical trick. While you do that, you are also changing the orientation. So if you use only a quarter wave plate, as you generate a phase mismatch between X and Y, you rotate the major axis. So to correct for that, what you have to do, what we typically do, is we combine half wave plate and quarter wave plate. We have both.
Okay. Thank you.
Thank you very much, George, for the questions. I think that they were very good questions, and I would like to thank also Giancarlo for the direct and very detailed answers. This is also something that we appreciate a lot. At this moment, I think that we should stop. It's 2:15. I would like to thank all of you for your participation and Giancarlo for this very nice contribution and very nice talk. I think that this opens the floor for future collaboration in experimental way in projects. I have some ideas like to email now to Giancarlo, and also to all of you to exploit, these Athena talks. Thank you very much. Have a nice weekend. Stay safe. We are going to continue next week within the framework of Athena talks with something different, like regarding the foresight technique, how you can use this technique in order to foresee developments in technology, like what kind of steps you should follow in order to see in the future, which is very important, like in the research, but in anything that we are doing as well. Thank you. Have a nice evening, and we will be in touch. Thank you. Bye.
Thank you very much. Bye. Bye. Goodbye. Thanks.
Bye.
George Kourmoulaki, send me your email, because we would like also to be part of the Athena talks.
Yeah, sure.
Thank you. Bye.